Here, we're starting with the concept of circular motion. It's the kind of movement where an object travels along a circular path. As we explore this, keep in mind two key ideas shown here: velocity, which points in the direction the object is moving at any moment, and centripetal acceleration, which always points toward the center of the circle, keeping the object moving along that curved path. Understanding these basics will help us grasp how circular motion works in different situations. Imagine an object moving along a circular path while maintaining a constant speed. Even though the speed stays the same, the direction of the velocity is continuously changing as the object travels around the circle. This change in direction means that the velocity is changing, and so the object is accelerating, despite its speed being constant. The diagram helps illustrate this by showing the velocity vector pointing tangentially to the circular path, indicating the change in displacement at a particular time.
Angular displacement is measured in radians. This angle is determined by the length of the arc, which is the curved part of the circle, divided by the radius. The radian is the standard international unit used for angles in the SI system of units. The key formula to remember is that the angle theta equals the arc length s divided by the radius r. A full circle in radians is equal to 2 pi radians, which is the same as 360 degrees. This means that when we measure angles in radians, the size of the circle doesn't affect the angle's value. Angular velocity measures how quickly an angle changes over time. We represent it with the symbol omega, and its unit is radians per second. When an object moves with uniform motion, angular velocity stays constant. Mathematically, it can be expressed as omega equals theta divided by time, where theta is the angle covered in that time frame.
In this example, all the skaters are rotating through a full circle at the same angular speed, meaning they complete one full turn together at the same rate. However, their linear speeds, the speed at which each skater moves along the ice, will differ depending on their distance from the center of the rotation. When all the skaters have the same angular velocity, the one who is farthest from the center of the rotation moves with the largest linear velocity. This is because linear velocity is the product of angular velocity and the radius, or the distance from the center. So, as the radius increases, the linear velocity increases too, even if the angular velocity remains constant. In this skating formation, the skaters positioned nearer the outside edge of the circle are moving faster in terms of linear speed compared to those closer to the center. When something rotates, its tangential speed, which is the speed along the edge of the circle, depends on how far it is from the center. The farther out you go, the larger the radius, and that means the linear speed is higher, even if the angular velocity, the rate of rotation, is the same everywhere. The direction of this speed is always tangential, meaning it points along the circle's edge, not toward or away from the center. Mathematically, this relationship is described by the equation v equals r times omega, where v is the tangential speed, r is the radius, and omega is the angular velocity. This helps explain why points farther from the center move faster in a rotating system. Centripetal acceleration is the acceleration directed toward the center of a circular path. It's what changes the direction of velocity as an object moves around the circle, even if its speed stays constant. This acceleration is always perpendicular to the object's velocity, because it points inward while the velocity is tangent to the circle. The equation for centripetal acceleration shows that it depends on the square of the speed divided by the radius of the circle. This inward acceleration is essential for keeping an object moving in a circular path rather than flying off in a straight line. Now, let's look at an alternative way to express centripetal acceleration using angular velocity. Instead of using linear velocity directly, we substitute v's with r times omega, where omega is the angular velocity. This substitution highlights how centripetal acceleration depends on the radius of the circular path. Even though the form looks different, it conveys the same physical concept, that acceleration is directed toward the center of the circle.
The resulting equation is AC equals R multiplied by omega squared. This form is particularly useful when we know the rate of rotation rather than the linear speed.
Centripetal force is the force that keeps an object moving in a circular path, always pointing towards the center of the circle. There are several sources of this force depending on the situation. Tension is one, like when a ball is tied to a string and swung around, the string pulls inward on the ball. Friction is another source, which happens, for example, when a car turns a corner and the friction between the tires and the road prevents it from sliding outward. Gravitational force is also a centripetal force, as seen with planets orbiting the Sun or satellites orbiting Earth, where gravity pulls them inward in their circular paths. Lastly, normal contact force, which is the force exerted by a surface that can cause circular motion, like when a roller coaster car goes around a loop and the track pushes it inward. These forces all act to change the direction of an object's velocity, keeping it moving along a curved path rather than straight.
Let's move on from the previous discussion and look at how the design of a curve affects vehicle safety and handling. When a curve is banked, the road is tilted at an angle that helps provide the necessary centripetal force to keep a car moving in a curve without slipping. This force comes from the horizontal component of the normal force that the road exerts on the car. Basically, the tilt of the road pushes the car inward, preventing it from sliding outward due to its inertia. For each banked curve, there's a specific speed where this horizontal component alone supplies the exact centripetal force needed, which means the car can safely navigate the curve without relying on friction from the tires. This is an important concept because it shows how road engineers can design safer turns that reduce the chance of skidding, especially at certain speeds. Centripetal force is the net force that always points toward the center of a circular path, and it's essential for keeping an object moving in a circle. It's important to understand that centripetal force isn't a new kind of force by itself. Rather, it's the result of actual forces like tension, gravity, or friction acting toward the center. The formula for centripetal force shows this relationship clearly. It equals mass times the velocity squared divided by the radius of the circle. This equation helps us calculate how much force is needed to maintain circular motion depending on the object's speed and the radius of its path. When we draw a free body diagram for an object in circular motion, it's important to focus only on the real forces acting on the object. We resolve these forces toward the center of the circle because the net inward force is what causes centripetal acceleration. This inward force, called the centripetal force, is the sum of all the actual forces pointing toward the center. It's also crucial to remember that there is no outward or centrifugal force acting on the object. Any sensation of being pulled outward is due to inertia, not an actual force. This understanding helps us analyze circular motion accurately using the forces involved. When we talk about period and frequency in circular motion, the period is the time it takes to complete one full revolution around the circle. Frequency, on the other hand, measures how many of those revolutions happen in 1 second. The two are inversely related, which means frequency equals 1 divided by the period. Another useful equation connects the speed of the object moving in a circle to the period. The speed equals 2 times pi times the radius of the circle divided by the period, which helps us understand how quickly the object moves along the path. Let's focus on the main points to keep in mind for the IB exam. You need to clearly state the direction of acceleration whenever asked, as this is crucial for understanding the motion involved. Drawing a correct free body diagram is also important, because it helps visualize the forces acting on an object and sets up the problem correctly. When working through calculations, remember to apply the formula for centripetal force, which is mass times velocity squared divided by radius. Lastly, always maintain a consistent sign convention throughout your work to avoid confusion and errors with direction and force values. Keeping these key elements in mind will help you approach problems calmly and clearly during the exam. To wrap up, remember that for an object to move in a circle, it needs a force directed inward toward the center.
This inward force causes acceleration, which always points to the center, even if the speed stays the same. While the speed doesn't change, the direction of the velocity does, which means the velocity is constantly changing. Using radians makes the math for these angular motions simpler and more straightforward, which helps in understanding and solving related problems. Overall, these points cover the key ideas about circular motion you should keep in mind.